the reports, and so we're going to be done. So 11.4 is conditional probability, and what we want to do is keep thinking probability like we've already been doing, but we're going to talk about how they're putting conditions on that probability. You know, we want to know the probability that a person would be attending a four-year college given that they're male. So you're only looking at the males, you know, those type of things. And we're going to use tables and probably not the tree diagrams today. We'll probably hold off till Monday for that to determine conditional probabilities. So this is a famous, well, kind of, I don't know, I guess in a way it almost feels like a trick question. It says, it's not Monty Hall's anymore, but it's the game show where they have the curtains and stuff, and you can trade what you have from curtain 1 to curtain 2, and now I can't remember the name of it. Has anybody ever seen it? It's usually like afternoon. What's it called? Can't remember right now either.
Let's make a deal.
Yeah, let's make a deal. That's it. So, and let's make a deal. This stuff happens all the time. It says a great prize is inside box 1, 2, or 3. We don't know which one. You choose box 1. You are shown that box 2 contains a rubber chicken. You're happy you didn't pick box 2. But you're given a second chance. They do that a lot on that game. You are given a chance to change your choice. Should you stay with box 1, or should you change to box 3 and justify your answer? Well, when you first looked at these boxes, there was a 1 out of 3 chance that what you wanted was in each of those boxes. But now, this one is gone. So, the probability changes. Now, this always seems really weird to me that probability changes here, but like it says, you want to change to box 3. There's a 1/3 chance that box 1 has your prize, and now there's a 2/3 chance that box 3 has the prize, and it has to do with the fact that they didn't show you box 3. They showed you box 2, and they did that on purpose because box 2 did not have the prize in it. So the chances that you should trade and go after the other one increase. Again, it's one of those things, it's called the Monty Hall problem. If you want to investigate it some more, you can go ahead and do that. But I'll let you know, it is kind of a trick question, and we're not going to talk trick questions, so I don't want to get too far into that. We're going to talk, here is conditional probability, this is how it works. So the probability that an event B will occur given that another event A has already occurred is called a conditional probability. So if I said I want to figure out the probability that students in first hour who have already made it to school today are wearing black, I would have everybody stand that has black on, and then I would count from the people that are here. I wouldn't count Carter. I'm missing Carter today, so I wouldn't count him as my total because my condition was all the students that are here, and he's not here, so he wouldn't be included in that total. So that would be a conditional probability. Conditional probability exists when 2 events are dependent. You have to be here for me to count you. There's a dependency there. You have to be in class. So you write the conditional probability of event B, given that event A occurs as, and we read this off as probability of B, and this straight up and down line is given. So that says the probability of B given A. And like it says, tables and tree diagrams can help you find conditional probabilities without having to do formulas. You know, you just think logically, what is the condition here, and how am I going to make sure that that happens as I'm finding the probability? So, up and down line, given. It says the table shows students by gender at 2- and 4-year colleges and graduate schools in 2005. You're going to pick a student at random. You're just going to grab somebody out of there. It says, what is the probability that they're female given that they've gone to graduate school? Well, I don't even really pay attention to the female part right off the bat. I want to know what's the given. The given is they have to be in graduate school. So I'm going to go over to the table, and I couldn't care less about the other 2 rows of data. The data I need is the people that are in graduate school. It said, given that they're in graduate school. Those are the only ones in graduate school right there. Now I go back and focus. Well, what do they want out of the graduate school people? They want those that are female. Okay. So these are supposed to go on the top of the total people in graduate school. All right, well, do a little math. Have a calculator. We'll find out what's the total number of people in graduate school. So we're going to take 1349 plus 1954. 1349 plus 1954. 3,303. Now, it might be reducible, might not, but this is one, since the numbers are so big, we would probably give a decimal answer anyway, or maybe a percentage. So 1954 divided by 3303. Math number 1, just in case. Look at that, you can't even reduce it, it's just a monster. So we're going to write that as approximately 0.59, or approximately 59%. So conditional probabilities, when you are given a table, they are not that difficult at all. They really aren't. So there we have it. Next one says, what is the probability that they're female? Do you see a slash there, or does it say probability that they're female given anything? So that means we use the whole table. We need all the females out of the whole table. This is not a conditional probability. This is, hey, find all the females out of the total. Well, we're going to have to go back and do some math. Let's see, our females. Oh, can't get that up high enough to write that at the same time. So I'll scroll this up when I get there. 2,462 plus 5517 plus 1954 over, I don't think I'm even going to write all 6 of them, I'll just put total. So we'll add all of the females, write down what we get, and then we'll add the remainder, which would be the males. So we've got 2462 plus 5517 plus 1954. 9,933 females. And then I'll just keep adding the males so I can get the total. Plus 1866, plus 4324, plus 1349. 17,472. Again, we probably want to use a decimal or a percentage. Talk about that. So approximately 57%. So why would they do these conditional probability pieces instead of just talking about the total? If they're interested in graduate school, I wonder. The probability that the females are in school here is 57%, but is the graduate school, we seem to have a lot more girls in there, a lot more females. Let's check that probability out. And in fact, the probability that they were female in graduate school was a little bit higher. So those are the types of pieces of data that colleges will look at to figure out, who do we need to try to get to come to our colleges more. So the got it here says in problem 1, we need to find the probability that they're going to the 4-year college given that they're male. And then B has a nice little question for us there too. And I think I'm going to give you candy partners and just let you give this one a try because I see some of you are already doing it anyway. So go ahead and read through and get started on it. I'll bring you a piece of candy and get your partner. again. Actually, what are the chances that 2 days in a row you would be the odd one out? So,
Let's find the probability.
let's calculate that. There are 2 pieces of candy. 1 group 3. Alright, that'll be for your partners there. Alright, candy up in the air. Find your partner or partners. There is 1 group of 3, the dum-dum suckers. Find them. Talk about our wonderful little probabilities here. Remember, got to leave your seat. Somebody wants it. Partner and all is good. I already talked about A. I didn't make it all the way around the room. Everybody's got A set? Okay, so for A, 4 years, given that they're male. So how many 4-year students were there? They had to be 4 years and they had to be male. So here, let me go back up here. I think some of you are kind of, did I pick the right stuff? Given that they're male, that's going to be our total right there, the guys. So 4 years, males, right there, 4324 over the total of males. All the way down the smart board. And the total for the males ended up being 7539. So what was your percentage, everybody? About 57, yeah. 0.57355. So remember, what comes after the line, I guess I think of it as a segment anyway, it is a segment, is the bottom of your fraction. You know, and those are the only ones you can look at. So 4 year, given that they are male, you have to go to just the males and look at that as your percentage. So for B, without calculating, given that a student is enrolled in a 4-year college, is it more likely for the student to be male or female? Talk to your partner about that one.
Yeah, for real. Where's that bottom number?
So sounds like there were no percentages being calculated here. Did you need percentages? No, because they said given that it's a 4-year college, you just look at those numbers and you say, hey, there's more females there. That's it. Megan.
How did you get 7,000?
Oh, was there a mistake in my key here? You're not getting 7,000 for the males?
Me too.
Oh. Oh, let's check. For the males?
What number are you supposed to add up for the bottom?
All the males. There's males. 7,539. So maybe you just punch something in a little wrong. 7,539. 7,539. 7,539. 7,539. 7,539. 7,539. 7,539. 7,539. 7,539. 7,539. 7,539. 7,539. 7,539. 7,539. 7,539. 7,539. 7,539. 7,539. 7,539. 7,539. 7,539. 7,539. 7,539. 7,539. 7,539. 7,539. 7,539. 7,539. 7,539. 7,539. 7,539. 7,539. 7,539. 7,539. 7,539. 7,539. 7,539. 7,539. 7,539. 7,539. 7,539. 7,539. 7,539. 7,539. 7,539. 7,539. 7,539. 7,539. 7,539. 7,539. 7,539. 7,539. 7,539. 7,539. 7,539. 7,539. 7,539. 7,539. 7,539. 7,539. 7,539 Oh, no, remember, the one that comes after the slash, that's your given. So if it said slash males, we're only counting up the males. That's it. So that was the condition. That's why it's called a conditional probability. You just look at the males. That's it. Everybody set now? All right. So conditional probability means we're not looking at all the data. We're just looking at a piece of it. Let's see, what was this? This was female. Because all we had to do was see that there are more females. Wasn't a matter of percentage once you just look at that condition that they have to be in the four-year college. Then you can just say, hey, this one's bigger than the other. You don't have to have you say where you are, because really the next problem is very similar. So I'm not going to do problem 2 with you because it's multiple choice. And I think you and your partner can make your way through that one. So go ahead and give it a try. Conditional probability, again, still looking at a table. So use that table. Yeah, you might need to go back and grab a calculator. Ooh, let me turn the lights up so you can see what you're doing. Start with here. That might be helpful. Yeah. Anybody need to borrow a calculator? Remember, look for the condition so you know which column or row you should be looking at. What's the condition of the problem?
Yeah, we did. I thought you guys were. Yeah.
This is the probability that a sample will be recycled. All the recycled.
Yeah, we did.
All the recycled. The condition is not that it's paper, right? The condition is that it has to be from the recycled waste. So that's going to be your denominator. That's going to be your bottom. There. A, B, C, or D? D? 57%? Yep. So if we take just the paper, 45.2, and look at it out of all the recycled waste, that'll be 57%. So it's kind of a word problem, but there's a table. The thing with the word problem is you have to see what's the condition here. You know, what's the big group that they want me to look at as I go through here. So go ahead and, well, 2A won't be much of a challenge now. Go ahead and do 2A and 2B. same numbers? Two A went faster because we already knew the total of the recycled waste. We already knew that that was 79.4. So all you were doing was changing your focus to the plastic, 2.1 divided by 79.4. And that one is 0.0264 blah blah blah. 0.0264. So we put approximately 3%. Tell your partner whether or not we had to change the given information. What I mean by given is the condition for B. I always wish they would change there and say, okay, now take a look at the non-recycled waste, you know. But this one is still talking about recycled waste. So we still have that same denominator. So if you're wondering, how is everybody getting all of this done so fast? They didn't have to do any more of the adding the totals together. It was always out of the recycled waste. And this one, talking about glass, was 3.2. So approximately 0.0403, which would be about 4%. So today, we got a good start on conditional probability, 43210. Know about using tables, conditional probability. So I'm going to give you one formula here to start us off for Tuesday, because we've got a 3-day break now. It's just something we're going to chew on between now and then. And that is, there is a formula. To me, it's kind of a silly formula. Because what do we always do when they give us and with probability? Tell your partner, what are we supposed to do when they give us and probability? That's what we're always supposed to do. So down here, when I think and, I don't care whether or not it's a conditional probability or not. You're supposed to multiply them together. But what they're saying is, let's just build this formula a little differently. Let's say we wanted to find this. Well, that's just algebra. Just divide both sides by P of A. That's the conditional probability formula right there. So you're not learning anything new. We know that if they say and, we're supposed to multiply. But we're saying, okay, let's manipulate this now. Let's just say what you really wanted was to find one of these two. In this case, we want to find the conditional probability. You take P of A and B and you divide it by the probability of A, and that would give it to you. So, thank you, partner. You guys did a great job. Helped each other through. This number should be used for this. This number should be used for that. So hopefully more and more, you're feeling more and more comfortable with probability, saying, hey, if I just don't overthink this, things are going to go really, really well. Because that's probability. Don't overthink. That is always the problem. As we learn more and more about probability, when you try to start going deeper than the problem wants you to go, that's the trouble. So always just focus on, hey, they want this, this is my total, bam, got my probability all figured out. No, let me double check, but I am certain that we held off on any of the tree diagram problems until the next assignment. Tables, kind of a table. Information chart there. tables, lots and lots of tables.